Hello, welcome back. I wanted to jump in real quick in my abstract algebra course to show one thing I didn't do in the previous video, which is how to find the inverse of a permutation. So let's do just that. Let me show you some examples of how to do it. So I'm going to take as an example the permutation in compact notation 1, 3, 2, 5, 7. This is an element of S7. And remember that this means this is the map that is sending, let's say, 1, 2, 3, 4, 5, 6, 7. Where are they being sent? 1 is going to 1 is going to 3, 3 is going to 2, etc. So what's happening in here is that 1 is sent to 3. Let's see where 2 goes. 2 goes to 5. Where is 3 going? 3 is going to 2. 4 is going to see in this notation, just 4 is not present. It means that 4 is going to 4. And then 5 is going to 7. 6 is also not present, so 6 is put. It's a fixed point. And 7 is going to 1. You see 7 goes back to 1. So that's the permutation. And then the inverse is just the map that reverses all those arrows. So if you look at this arrow and I want to know where 1 goes, you just have to find 1 and see that 1 came from 7. So the inverse map has to send 1 back to 7. Where did 2 come from? 2 came from 3. So now I know that 2 is supposed to go to 3. Similarly, 3 is supposed to go to 1 because 3 came from 1. So 3 is supposed to go to 1. 4 came from 4, the same way that 6 came from 6. 5 came from 2, and 7 came from 5. So it's that permutation. And I can just write it also in compact notation so that I'm going to write it here to say that, well, that the inverse of 1, 3, 2, 5, 7 is this one, which is given by, well, just follow the cycle. 1 goes to 7, 7 goes to 5, 5 is going to 2, 2 is going to 3, 3 is going to 1, so it closes the cycle. Now, notice that I could have just done that straight from 1, 3, 2, 5, 7. If I just want to avoid this whole thing, I don't need to write all of that. I can just see that you write the inverse. If in the map itself 1 goes to 3, what I want to see is what mapped to 1 and 7 mapped to 1. So I just have to reverse that. So instead of like usually this notation means that 1 goes to 3, 3 goes to 2, 2 goes to 5. So I have to go in the other direction. So 1 goes to 7, 7 is going to go to 5, 5 is going to go to 2, and so on. So what we have is that 1 goes to 7, working backwards, and then 7 goes to 5, and 5 goes to 2, and 2 goes to 3, and 3 goes to 1, so it closes the cycle. So that needs to be the inverse. Let me do one different example. Let me just do it actually in the next page. So, for example, if I have 1, 2, 3 times 4, 5, what is the inverse of this permutation? Well, the inverse will be I just go backwards. So I'm going to start with 1 and see where 1 came from, which in this case is 3. So 1 came from 3, 3 came from 2, 2 came from 1, and excuse me. Okay, through 2 came from 1, so that closes that cycle. And then let's see where 4 came from. Now you see that 4 came from 5, so 4 goes to 5, and 5 came from 4, so the inverse of 4, 5 is 4, 5. So this will be the inverse. Let's check that that is actually the inverse. So how do I know that that is the inverse? I'm going to multiply them together. If this time, if 132 times 4, 5 is the inverse, when I multiply them together, I'm supposed to get the identity. So let's see what happens with this permutation, going from right to left. So where does 1 go? 1's stable here. 1 goes to 3, and then 3 goes to 1. So 1 goes to 1. Let me just write this, although we usually do not write that. But let me just, for clarity, say that 1 went to 1. Let's see where 2 goes. In here, 2 is stable. 2 goes to 1, and 1 goes to 2. So that tells me that 2 goes to 2. How about 3? 3 goes to 2, and then 2 goes to 3, so 3 is stable. 4 goes to 5, and then 5 goes to 4, so 4 is stable and 5 is stable. That is just the identity, and therefore we have checked that one is the inverse of the other. So anyway, that's all I wanted to show you here, an example of how to build the inverse of a permutation. And next we're going to talk about the alternating group.